Okay, so we're just going to round out with these a really typical type of questions here. Um, so a lot of these questions you will be asked to make a word out of other words, and so we're not looking for like anagrams. We're just looking for rearrangements of the letters. They don't have to actually make a real English word. It's just gonna be the number of ways to rearrange it. So we'll start with the easy case. How many words can be made from the letters in Janet? So what we have here is a 5-letter word. Basically, we go right back to the start of how we would approach something like this. We're looking for the rearrangements. You could do your whole slot method here. I would say we'd pick the first letter. There's 5 possibilities. Now 1's gone, so there's 4. Now we only have 3 left, 2 left, 1. So you could work that out. You could think of this as 5 total objects, the letters J-A-N-E-T, and you are arranging 5 of them. So, another way that we could look at that is your 5P5 formula and calculating it that way. Using a calculator or whatever. Or if you think back to just the definition of what a factorial is, we could also just use the number of ways to arrange all 5 objects. But these are all the same thing. It's all just tying the same concepts together. That one's 5 factorial. So whichever you prefer, these are all equal to, let me find my factorial button, 120. So there's 120 words. Not all of them are words, right? Tenja is not a word, but it is a rearranging of these letters. All right, question 2. How many words can be made from the letters in Chidi? And props to you if you figure out my reference at this point. The third one will also fall in line with these. Okay, so in this case, we do have a little bit of a snag because all of the arrangements that we've seen so far have required that we have distinct objects. And here we clearly do not have distinct objects. We have repetition. So the way that we can view this is to actually sort of pretend that they are distinct. So what we're going to do is instead look at, let's say, this CH, and then maybe I'll do an I1D and then an I2. So now they're all of a sudden 2 different I's. They're different things. So the arrangements here, there would be your 5 factorial for this one. The exact same as the Janet, right? It's the same number of letters, and so there's the same number of arrangements. But if we look at a few of the pairs that might show up in this, so for example, if I have this arrangement here, this original one, it's actually the exact same arrangement as this one. They're the same thing. If I write them in alphabetical order, so C, D, H, I1, I2, it's the same thing as C, D, H, I2, I1. So actually, like if we just flip the I's around, which is, because there's 2 of them, there's like 2 different ways we could arrange it as either I1, I2 or I2, I1. Basically, every single pair of I's is showing up twice in this count when we think of them as being distinct things. So what we're going to need to do at that point is divide by 2, because every ordering, like every location for the I's actually shows up twice. That's a really terrible way of saying it, but I'm tired. So every I locations, I don't know how to say that better, shows up exactly twice. So we actually have to divide by 2 to like collapse them back onto each other. So what we end up getting is actually 5 factorial divided by 2. That was 120. I already had that number from last time. Over 2 is going to be 60. So that's actually going to be the arrangements here. And so what we'll have in this scenario is arrangements with repetitions. So that's what we're looking at now. All right, so to summarize what we just had there, when we were looking at the word, so it was Chidi, so a 5-letter word with a repetition of 2. So if you have a set of n objects where r of the objects are repeated, and we have k1, comma k2, k3, all the way up to some kr. So those are the numbers of all of the repeats, basically. So if we have all these repeats, then the total number of arrangements is going to be, so that n factorial, which would be the count if we treated all of those repeats as distinct individual objects. And then we have to divide out the arrangements that can occur within those repeats. So if there's like 4 e's in a word, there would be 4 factorial, which is 24 arrangements that are actually all equivalent to each other. So we'd have to divide them out to sort of not count all the repeats, basically. So for example, we had this Chidi here. So it's 5 letters, n is 5. I repeats, so there's only 1 repeat. So the number of repeats is 1. And then the k that goes with that repeat, it repeats twice. So the k is going to be 2. And so in that expression there, it's just going to be that 5 factorial over 2 factorial. So before we just used over 2 because we said it was referring to the 2 arrangements I1, I2 versus I2, I1. But yeah, if there's more things, there's going to be more equivalencies that we need to sort of wash out. So that was the first example we did. This one's obviously got a lot going on. So we're doing this whole mashed together word, Eleanor Shelfstrop. And so what we're going to do is find the total number of words that can be made from this. They're going to be very long, terrible words because this isn't even a word itself. And I don't think there's a single one of these arrangements is going to be an actual English word, but that's not what I mean when I say word. So what we've got to do is find the total number of objects here. So my n. So n is the number of letters, which I have to be careful here because I'm pretty tired. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So 17. And so now I need to find my repeats. So I'll just use different colors. I've got 1, 2, 3 E's. So I'm going to call this K1 is 3. Maybe find a different color. I definitely have more here. I've got 3 L's. So K2 is also 3. I've got 2 S's. So I'll call my next K value K3 is going to be 2. I mean, I could call them KE, KL, KS if I like to, because that way they'll actually, refer to the exact objects I'm repeating here. I've just got the 1 A, there's 1 N, there's 2 O's. And so that's going to be K4 is 2. And R, there are 2 R's. And I think that's all of them. So my K5 is going to be 2. So the formula, my number is just going to be 17 factorial. And then just grab all those numbers on the left there. So 3 factorial, 3 factorial. So I don't have to get caught in that whole K1 through KR language there. I really just need to count the repeats. 3 factorial. Oh, no, that's a 2. 2 factorial, 2 factorial, 2 factorial. So colorful. Yeah, so I'm just going to work this out. Yeah, you'll probably want to actually just punch this whole thing in, because I have a feeling 17 factorial is going to be massive. So what I might want to do here, I'll just show you how I would punch this in a calculator. It might even be worth, you could probably simplify the bottom here and get a number. So that should be 6 by 6 by 2 by 2 by 2. It's 288. Yeah, and now that 17 factorial divided by 288 is, all right, I'll tell you what my calculator says here. So it's saying 1.235, a bunch of decimals, and then I can see this little tiny times 10 to 12. So that's kind of more or less what my calculator looks like. Like the 12 is massive compared to that times 10. So this is scientific notation. So what that actually means is, move the decimal place over 12 times. So if I did that, yeah, so I'm getting a pretty massive number. I think it actually ends up being like a whatever, yeah, it's like 1.235 trillion essentially. There's very many ways to arrange this thing. So if I actually carry a few more decimal places, my calculator doesn't love this. It doesn't know what the next 3 numbers are, so rounding will just put them at zeros. That's why I'm using the little squiggles instead of an exact equal, because the number's just a little too big to get right down to the exact value. So yeah, many, many, many ways to arrange. All right, so just one more question. So as of this day in 2020, there are 7 red stripes and 6 blue stripes on the American flag. So I say that to be specific because, well, how many ways could those stripes be arranged? So yeah, so let's say we potentially shuffled them around and made a less stripy change color pattern. So maybe we lump a few reds together, put some whites together, just some sort of rearrangement here. Yeah, so basically there are 13 places for the stripes. Or like 13 objects, or 13 stripes. I guess it would be a maybe even easier way to think it if I don't want to think of that like putting things in places method. So there's 13 stripes. And as far as repetitions, let's be color specific here. So repetitions, we've got 7 red and 6 blue. So those are our repetitions across the bottom there. So yeah, the total number of ways of doing it is actually just 13 factorial over 7 factorial, 6 factorial. We calculate that. I'll just use a calculator. So there are 1,716 different ways that we could arrange those stripes. So just a little teaser for what comes after this section, the last method of counting. Another way that we could actually think of this is of the 13 stripe locations, what we're going to do is choose which 7 we want to be red. So that'll just be a little intro to the next counting section, where you have a big collection of objects that are distinct. So in this case, the objects would be the 13 stripe locations. They are all different locations. But what we want to do is choose a collection of them And in this case, if we choose them and just write them all red, it doesn't really matter what order we actually choose them in, because once we paint them all red, no one's going to know which one we did first or not. So the word choose is going to be really different from the word arrange. Choose is going to imply that order doesn't matter, but this is a different way that we could actually view this exact same problem. And it's going to lead into the formula that we'll see in the next chapter, the next section.